Hello everyone, my name is Todd Barron and I'm the meteorologist in charge here at the National Weather Service in Huntsville, and welcome to the Huntsville Science Fair, and thanks for your interest in weather. So much like everyone else you're going to hear from today, we are scientists. We study and measure various elements of the atmosphere to help you understand what the weather will be like today. And understanding what that weather can be like today helps us understand what it could do tomorrow and clue us in on climate changes and impacts decades from now. So in order to be a meteorologist, whether you want to forecast weather for the National Weather Service on TV or in the military, or at a university, you'll need a 4-year college degree, which will involve a lot of math and science. But don't worry, it's very rewarding, knowing that your forecast will have a direct impact on protecting life and property. So thanks again, enjoy this presentation.
Hello, and welcome to this Introduction into Weather webinar. My name is Jessica Chase, and I am the Warning Coordination Meteorologist at the National Weather Service Forecast Office located in Huntsville, Alabama. Today's talk will go over some brief topics on basic meteorology, such as who the National Weather Service is, a brief intro into what causes weather, and what different weather hazards you might face, especially living in the Southeast. So first things first, who is the National Weather Service? The National Weather Service is a government agency that is made up of thousands of employees across the country. There are 122 weather forecast offices nationwide, including Puerto Rico and Guam. Each office has a subset of counties or parishes, so we can focus on specific areas called our County Warning Area, or CWA. The Huntsville office is located within the Tennessee Valley, and we cover 11 counties in northern Alabama and 3 counties in southern Middle Tennessee. There are NWS meteorologists at work 24 hours a day, 7 days a week, even on birthdays and holidays. Our mission is to protect life and property, so we are always there making sure everyone is weather ready. In addition to the weather forecast offices, there are several regional and national centers across the country. We have 6 regional headquarters that focus on coordination between local offices. There are river forecast centers, which forecast for points along major rivers and streams and what the flooding potential is. There are center weather service units that work with airports to forecast for airplanes and travel. And lastly, there are national centers that monitor everything from hurricanes and severe storms all the way to space weather. Anywhere you might want to live in the country, there is probably a weather service office nearby. From day to day, this is what we do. We analyze weather forecast models and current observations to literally predict the future and tell you what the weather could be like up to a week away. Whenever there is impactful weather, we issue watches, warnings, and advisories to let you know when you may be in danger. On quieter days, we are able to do research to help answer questions we have, and also go into the community and work with local officials, schools, and the general public to increase weather awareness and education about weather impacts. More specifically, the modern meteorologist has to do a lot of different jobs at once. At our office, we work with all of the national and regional centers we discussed earlier to focus on local forecasts, meaning we only worry about the Tennessee Valley and try to be as specific as possible. Working on forecasts for airports, rivers, fire impacts, and our coastal offices even forecast for the ocean. We use observations like weather stations, weather balloons, and radars to issue 7-day forecasts and help local government officials make choices, which we call decision support services. Here are some of the sources of information we use multiple times a day to help us make the best predictions and forecasts possible. From weather radars to satellites, measurements from surface weather instruments like thermometers, barometers, and anemometers, radio sondes lifted by weather balloons, and lastly, computer models which forecast for future weather patterns. Now let's talk about each one of these in a little more detail. Let's first look at the Doppler radar. Doppler radars are especially important to meteorologists anytime there is precipitation in the area. Radars look like giant golf balls on top of a ladder. The golf ball is called a radome, and inside this fiberglass sphere, there is a giant satellite dish. The radar sends out beams of energy that strike objects suspended in the air, like rain, hail, and snow. As they strike these objects, the energy is scattered and some of it is reflected back to the radar. The larger the object, the greater the amount of energy. The radar is able to translate this into an image that meteorologists look at to determine what kind of objects the radar beam hit. The radar is located on the ground and points up and out to help us see storms and rain from the bottom. But what about the tops of storms? For that, we launch weather satellites on rockets and put them out in space. These satellites are constantly taking pictures of the Earth's surface, which we are able to look at and see where the clouds are and where they are moving. These satellites are over 22,000 miles away in space, but are able to send us pictures with such fine resolution we can see each cloud as it develops, matures, and dissipates. Our satellites are called GOES, which stands for Geostationary Operational Environmental Satellite. Geostationary means that as the Earth rotates, the satellite rotates at a speed so it sends pictures of the same area every time. Imagine I was spinning in a circle and you had to run around to make sure you were always looking at my face. That is what the satellites are doing to planet Earth. So what about between what the radar sees and what the satellite sees? There is a lot of air to cover and a lot can change between these two layers. For that, we turn to weather balloons. These are sensors attached to a balloon that tells us the temperature, dew point, pressure, wind speed, wind direction, and height from the ground all the way up until the balloon eventually pops. The first step is to fill the balloon with either hydrogen or helium at one of our offices. Not all weather forecast offices launch balloons. And this is done twice a day, once in the morning and once in the afternoon. Once the balloon is filled with a gas that is lighter than air so that it floats, the next step is to attach the sensor and take it outside away from any buildings, trees, or power lines that it could get caught onto. Once you are placed far enough away to avoid it getting caught, you let go and let it start taking measurements as it floats up. In about an hour, there will be a whole picture it paints, which acts like a slice taken through the atmosphere and allows us as meteorologists to see what changes at different heights, which is important to know what is happening now to better predict what will happen in the future. Now think about every point on Earth and then every point in the atmosphere above the Earth's surface. And imagine you are a meteorologist trying to predict what would happen at each one of those points every hour or 6 hours for the next 7 days. Seems almost impossible, right? Maybe for the human brain. So the human brain invented supercomputers that can do so many calculations per second that in only a matter of hours, thousands of equations are run to calculate what each layer of the atmosphere will look like every few hours for the next week or more. These equations used are different for each weather model, and each one is only a best guess of what could happen. No forecast model is 100% all of the time or at any time. It is up to the meteorologist to look at all of this information and make the best decision using all of this input. Now let's practice on the next slide. Pretend you are forecasting for the middle of the state of Texas, shown in the map. Your job is to figure out where the red X will be, and this is 4 possible locations from 4 different models. Which one do you believe? It's hard to say, and this is a challenge that meteorologists face every hour of every day they are at work. One way is to go back in time and see which model has done with predicting where X will be so far. Another method is to average them all together and try and pick a solution that is close to each one. A third option is to see which location is most frequently shown by each model, which looks like it would be somewhere near the middle Texas coast between location 3 and 4. So we've looked into who we are at the National Weather Service and the different tools we use. Now let's take a look into some basic meteorology and answer the question, what causes weather? If you guessed the sun, you're absolutely right. We know how important the sun is to our solar system, but did you know that it is also responsible for the weather we observe on Earth? Let's take a look at why that is. We get our heat from the sun. As the solar radiation passes through the atmosphere, it is absorbed by the Earth's surface. The Earth emits some of this radiation into the atmosphere, and that is what causes the air to warm up. This is the reason why, most of the time, the air gets colder as you move up in the atmosphere. If it were up to the atmosphere, there would be the same heating no matter where you were on Earth. However, because of the Earth's tilt, it is impossible. The sun heats the Earth unevenly, with the most radiation received at the equator, and then decreasing amounts of radiation as you move towards the poles. Additionally, the Earth's rotation around the sun impacts the amount of heating, and this is also what gives us our seasons here in the continental United States. Another reason that even heating is impossible over the Earth is because land and water heat differently. Land heats faster and to a higher temperature than water, but it also cools faster and to a lower temperature than water. All of this uneven heating leads to uneven pressure distribution across the Earth, with areas of high pressure and areas of low pressure. Think of areas of high pressure having a lot of air over it, while areas of low pressure have a lower amount of air. Much like the even heating, the atmosphere also wants to have the same equal pressure everywhere. It is always trying to maintain some equilibrium, but as we've seen, that's just impossible. And because of that, air moves from high pressure to low pressure to try and even things out. We call this moving air the wind. Let's take a little closer look at high pressure and low pressure systems. Areas of high pressure are typically associated with colder air aloft. Cold air is more dense than warm air, which makes it sink. As it reaches the surface, the air, or wind, spreads out. We call this spreading out diverging winds. The sinking motion of the colder air also causes any lingering cloud cover to evaporate and prevents any new clouds from developing. This leads to fair weather with high pressure. Conversely, low pressure is associated with warm air. Because warm air is less dense than colder air, it rises. Also remember that wind blows from high pressure to low pressure. These winds come together at the surface, and we call these converging winds. When the winds meet, they have nowhere to go but up, and then this increases the upward motion. This upward motion helps clouds develop and can lead to precipitation developing. Here's a look at a typical weather map. We see the blue H representing high pressure and the red L representing low pressure. There's another important feature that leads to more active weather, and that's called a front. Fronts are simply boundaries separating different air masses. Where cold air is replacing warm air, we have a cold front represented by a blue line with triangles. Where warm air is replacing colder air, we have a warm front that is represented by a red line with half circles. Did you know that the direction those triangles and half circles are pointing is the direction the front is moving? So here, the cold front is moving eastward and the warm front is moving northeastward. Let's look at the different weather associated with cold fronts and warm fronts. Remember when I mentioned that colder air is more dense than warmer air? Well, because of this, the colder air behind a cold front that displaces the warm air can move more quickly. This creates a more extreme upward motion and typically leads to thunderstorms. Meanwhile, because warm air is less dense than cold air, warm fronts move more slowly. This creates a more gentle upward motion, and we tend to see mainly rain and weaker thunderstorms associated with warm fronts. With all of this information about what meteorologists do and how they do it, let's focus on the different types of weather that meteorologists predict and what you can do to be safe from each of these types of weather. The first one is thunderstorms. This picture shows an average of how many days per year each location in the United States of America sees a thunderstorm. We are in north central Alabama, where there are typically between 50 and 60 days that have a thunderstorm per year. Because of that fact, it is important that we know how best to be safe if one passes over or near us. If a thunderstorm is especially strong and threatening to your life or property, then we classify it as a severe thunderstorm. By definition, this means that the thunderstorm is producing hail over 1 inch in diameter or winds over 58 miles per hour. A tornado would also make a storm severe, but we have a different warning we issue for tornadoes than severe thunderstorms because on average, tornadoes can cause a lot more damage. Just because a tornado is more damaging, that doesn't mean that severe weather warnings should be ignored. Severe thunderstorm winds can be incredibly damaging, especially if it is what we call a microburst. These types of incredibly damaging winds can knock down trees and power lines and damage well-built structures like schools and homes, or even airports like this shown in the image. The second definition of a severe thunderstorm is hail over 1 inch in diameter. Hail forms when rain and ice bump into each other in the rising motion of a thunderstorm and stick together and then refreeze on contact. This tiny particle will keep going up in the rising motion and get another layer of ice on top of it until it becomes too heavy for the rising motion and then falls to the ground as hail. Because of this pattern, the stronger the rising motion in a thunderstorm, which we call the updraft, the potentially larger the hailstone. By definition, every thunderstorm also has lightning. This means that every lightning strike also has thunder. How many people have heard of something called heat lightning before? Well, there's actually no such thing as heat lightning. It is only lightning in a thunderstorm that is too far away for you to hear the thunder. If you do find yourself near or in a thunderstorm, you need to seek shelter indoors immediately. Lightning can strike up to 10 to 15 miles away from a thunderstorm, so even if it isn't raining on you, you can still be struck. This means it is best to wait 30 minutes without any thunder before going back outdoors. One of the scariest types of severe weather is tornadoes. A tornado is a violently rotating column of air that reaches from the bottom of a cloud all the way to the ground. If the column of air does not reach the ground, then we call it a funnel cloud. If meteorologists determine that a tornado is likely, then we will issue a tornado warning. This means that you need to take immediate action, head indoors, and go to the center room of the lowest level in the building. Stay away from windows and doors, as these can swing or break open and allow debris in that can hurt you. Another part of our job is to track damage caused by storms and determine whether the damage was caused by a thunderstorm or a tornado. If we determine that it was a tornado, then we rate the strength of the tornado by the enhanced Fujita scale, which estimates the maximum wind speed in the tornado based on the damage that occurred. An EF0 tornado is weaker and causes some minor damage to tree limbs and roofs, and the higher the number, the more destructive the tornado. The highest level on the EF scale is an EF5, which completely destroys all buildings and can even tear pavement off of a road. So what can you do to help save your life if you are in the path of a tornado? Seek shelter. If you have a special storm shelter or a basement, that is the best option. If you live in a mobile or manufactured home, contact your county's emergency manager and see where there is a public shelter closest to you. Head indoors as quickly as possible, and again, go to the most interior room at the lowest level. You don't want to shelter outside, you don't want to be in a boat, and you definitely don't want to be in a car if you're in the path of a tornado. In the southeast especially, but across the country, another type of life-threatening weather impact is flooding. Prolonged heavy rainfall can cause rapid rises of water in places where water doesn't normally belong, on the roads, in buildings, across highways, and this water may be moving very quickly. Flooding is incredibly dangerous, and only 6 inches of water can sweep away a person. and it only takes 2 feet of moving water to sweep a car off a road. Because of that danger, we like to say turn around, don't drown. Meaning that if you are in a car and you see water covering the road, turn around or else you may drown. Do not ever play in floodwaters because there could be bugs, snakes, fire ants, and raw sewage in there, as well as potentially live wires that you cannot see. Regardless of the type of weather in the forecast, it is always important to have a disaster supply kit ready to go. Here is a list of some items you should consider to include in yours at home. Once again, thank you for attending this presentation. For any questions or comments, please contact me at jessica.chase@noaa.gov. Have a great day.